Hey, welcome back. So far, we've discussed the concept of a power series. We've played around with this base power series representation of 1 over 1 minus x. And part of you might be thinking at this point, wow, we've gotten a lot of work out of this single representation right here. Well, actually, this video will show you we're not even close to as much as we can do with this single representation. What we're going to do is formally define the ways that we can manipulate and combine power series to create representations of functions on certain intervals. And here we have three main ways that we manipulate or combine power series. So importantly, the setup for this is we have two different power series here. We have the ones described by the C sub n coefficient and the D sub n coefficients. Both of these converge to the functions f and g respectively on an interval I. Then what we can do is we can construct a power series by adding or subtracting these coefficients of these power series to create a new series that converges and represents the functions of f of x plus or minus g of x, depending on whether we're adding or subtracting those coefficients in the power series on that same interval. The example that I do right after talking about these properties will show you how I'm going to implement number 1. But for 2 and 3, we've actually already seen examples of that. And after I talk about them, I'll go back and show you the example that we've previously looked at with 1 over 2 plus x and how we use these, and just to give it a very rigorous definition and what you're allowed to do. So if we consider an m value that has to be an integer, so this sign, just say m is an integer and it has to be positive. And then b, which is going to be this added coefficient of sorts, can be any real number, so negative, positive, 0. Then if we multiply a known convergent power series by these values right here, b times x to the m, so m is a power in this case, so strictly positive or 0 actually, and this needs to be an integer, b can be any real number. Then this series, which is the same as this, we know, but that we know that converges to this function where we take the convergent function of this power series and multiply it by this power of x and this coefficient b. We know that that new function created there is convergent on I. And again, I'll show you how we use that previously, just to make sure it's very clear. A lot of this notation can get kind of crazy at this point. But then also for number 3, we have this way of composing, and you've seen this too. But for the same setup for the values of m and b, what we can do is plug this b x to the m, so this coefficient b and this power of x inside, so taking over for the spot for the x here. And then we know that that will converge to whatever f, this original function here, composed of b x to the m for all x values such that b x to the m is on I. And because I'm going to need this board space, I want to relate back to these as I'm doing my future examples. I'll just give some words here. So we'll just call this the sum and difference property of convergence power series. We'll call this the multiplication by either a constant and or a power. And so that's just for the b for being a constant and this power being this power of your variable x right here. And then this we're going to refer to as the composition because we're plugging in this b x to the m inside the function. And again, the notation can be a lot, but I want to make this clear what these say that we can do and clarify what rules we've previously used. So we have this truth right here, and we vigorously have defended that. But if we wanted to manipulate this to make a new function, in this case, what we're looking at is f of x equals 1 over 2 plus x. So we want to manipulate this power series so that it will represent this function right here. And this is how we did it. So we have this function, so we'll take this power series right here and starts at 0 to infinity. I'm going to put parentheses here for the x because I want to plug something in, or we did plug something in there. But what I can do, so what this property right here, so the multiplication of a constant or a power, I'm just going to multiply by a constant here. You're allowed to multiply by this 1/2 right here. I know the resulting power series is going to represent a function, which is just this version multiplied by 1/2. but then I'm also allowed to multiply by a constant and a power of x inside here. This is the composition rule. And what we did here was multiply by 1/2, so that would be a b value right here. And then our power of x that we use was just x to the 1 power. So then what properties 2 and 3 are stating is that this power series right here will converge to it's 1 over 1 minus whatever we've composed right here, but I'm just going to throw our 1/2 that our factor we've multiplied by here. So this is multiplying this by 1/2. And then I've plugged in for the x right here, this composition, I've plugged in negative 1/2 times x. And I won't show all the work again, but when we clean this up, because of how we wanted to set this up, this will finish up and simplify to be 1 over 2 plus x. And then finally, what this composition statement says, especially at the end right here, is that now your intervals of convergence may change given what your composition is. So what we need to do is analyze that interval of convergence for when this is on I. Again, the b times x sub n is represented by this 1/2 x. And so again, I won't go through all the work here, but we put this in place of x in this interval that we are already converging on for x. The absolute value of x is less than 1. The negative goes away. We clean things up. And again, won't talk in detail about this, but this changes the interval of convergence and the radius of convergence, actually. So now we're going from -2 to 2. I think it's important to take a moment to step back, because as you develop these properties and abilities with different mathematical objects, the real important thing is to remember what you can or cannot do. And I just want to really emphasize these two things that we are allowed to do. We're allowed to multiply by constants, any real number in this case, and powers of our variable x in this case. We're allowed to do this by property number 2. And then we're also allowed to use this trick of composition, which is a really important manipulation in this case, and that is allowed by property number 3. But property number 3 also has this important caveat where you now need to rethink about the interval of convergence. All the other ones don't change the interval of convergence, but number 3 is all about now that you've composed something into this power series, you need to check your interval of convergence to make sure it doesn't change, or often it will. All right, let's look at this beautiful example here, which will have us actually use all 3 properties that we were just talking about. We're looking to construct a power series for f of x equals 1 over x minus 1 times x minus 3. Very importantly here again is be careful with what you're allowed to do or what properties we have. We actually have not yet talked about the multiplication of 2 functions or 2 power series. Hint, that's coming up very soon. It's not quite as nice as you might have wanted. But in this case right here, I can attack this without even worrying about the multiplication of 2 different power series. What we're going to do is we're actually going to rewrite this rational function here as 2 separate rational functions being added together. And we're going to use partial fractions to do that. Yes, partial fractions are never going to go away. They're a beautiful manipulation technique for simplifying rational functions. And at this point, you've done partial fractions many times, so I'm going to go fairly quickly through this. This is our first setup. Multiplying each side by x minus 1 times x minus 3 will give us that 1 equals a times this denominator of x minus 3 and b times x minus 1. When I distribute this and clean things up, I would look at this as a plus b is the coefficient for x, and then our constant coefficient is negative 3a minus b. And what that means is if this equals this, well, I know my linear coefficient here is 0 because I have no x's over here. So I know a plus b must equal 0. And when I do that, I always automatically say that means that a equals negative b. So they're just opposites of each other. That's the only way they're 0. And then I know that negative 3a minus b equals 1. And then what I'm going to do is make this substitution here. So negative b is a. Well, that's perfect. So I'm just going to write that. Now this becomes negative 3a plus a equals 1. which is negative 2a equals 1. So a equals negative 1/2. And we know b is just the opposite, so we know that b is a positive 1/2. So our first important step is down. We have this partial fractions decomposition. And so we're going to rewrite this as the a, which is negative 1/2 over x minus 1, plus the b is 1/2 over x minus 3. And what we're going to do, and again, trying to sell you on, it's pretty crazy how much we're going to get out of this single representation right here. But for both of these, we're going to manipulate this power series that we know. And we know this, I should say this too, just so we don't get messed up here. We know this is on negative 1 to 1, or the other way of writing this is the absolute value of x is less than 1. Either of those will work. This will probably be easier when we're looking at our interval of convergence later, but I digress. So what I want to do now, again, thinking about our properties, is I want to rewrite both of these in terms of this using multiplication of constants or powers of x, or using some kind of composition in the manipulation. All right, so in the effort to rewrite both of these as compositions and multiplications of constants of this function right here, what I'm first going to do is reverse the order on both of these. I can flip this denominator, x minus 1, to be 1 minus x. I just get out a negative, so they're just opposites of each other. It actually works out really well for this first term. So I get that this function f of x equals, so I'm going to rewrite this as 1 minus x. There's a negative that comes from that. I'm just going to apply it to that negative to get a 1/2 right there. I don't have a negative here, but I'll just put it out front. And so I have this 1/2 over 3 minus x. This first function's already done for me. I now know that all I need to do is multiply this by 1/2, this power series by 1/2 to represent this term. This term needs a bit more work because of this 3 right here. But just what I can do is I simply multiply the numerator and denominator by 1/3 in this case. So if I do that, again, this first term I'll just keep, maybe I'll write it like this, just to make it really clear. You don't have to write it like this, but that's just 1/2 times this 1 over x. And in this case right here, I'll just keep this as, well, maybe I'll throw this out front too. Negative 1/6 here, and then I get a 1 up here, and this becomes a 1. Again, that's the attack of this 1/3, is to create that to be a 1, because I need that to be exactly the same as that term. And then here what I get is negative x over 3. And so what I have done here for each of these terms, once again, to try to really make sure this settles in and so you know what you're allowed to do and what you can't do, is I'm thinking about this given power series right here. I'm first going to multiply by these constants of 1/2 and 1/6 respectively. And then I'm also, in this case of this second term, I'm going to need to think about the composition of x over 3. Those two moves again right there are using the second and the third properties of combining power series together. This composition is going to have effect on the interval of convergence, and we'll talk about that in a second. But importantly now, what I would need to do is I'm going to implement the first property, which allows us to add or subtract known power series or convergent power series together. And so what I'm going to do, this was all just the setup. I'm going to show you the straightforward construction of a power series that represents this, given this work that I've already put in. So first thing, we're going to construct two separate series for each of these terms. So what we know for this first one right here is that if I multiply this known power series, or this known function and power series, by 1/2, this will converge to this power series right here, where I throw this 1/2 right here, and this will be on that same interval from -1 to 1. In the second case right here, if I multiply this out front by the 1/6, and then I compose it with this x over 3 right here, then this will converge to this power series where I have this coefficient of 1/6 and I have this x over 3n on the inside. The difference being here, and this is an important difference, is that this converges not on the same interval, it converges on the interval where x over 3 is less than 1. And it doesn't take too much to analyze the fact that this means that the absolute value of x would be less than 3. So again, that first property says, if I know I have these two power series that converge on these intervals to these functions right here, again, which I've developed from the second and third properties right there, then the subtraction of those power series converges to these functions being subtracted from each other. And so I'll kind of consolidate these a little bit. So that's 1 minus x and minus the 1/6 over 1 minus x over 3. And given my work previously right here, all this is a version of this original function, which is 1 over x minus 1 times x minus 3. And so this can be represented by this power series. I'll combine these together just using my properties of infinite sums right here. Just so you know, what I'm going to do is I'm going to distribute. It's not distribution. I'm going to apply this exponent of n to both of these. Clean this up. So let me I'll take a couple steps with this just so it's not too crazy. So n equals 0 to infinity. I'll do 1/2 x to the n minus, so I'm going to take that. I'll throw this 3 to the n. So 6 times 3 to the n times x sub n, or x to the n right there. Again, just kind of taking off this constant piece and putting it with this constant factor right there. And then I think it'd be nice to clean this up by factoring out this x of n. So the power series, let's write this in a better order and turn this around. So this function right here, x minus 1 times x minus 3, can be represented by the power series from 0 to infinity of, again, factoring out the x to the n power right here. 1/2 minus 1 over 6 times 3 to the n, x to the n. And you know, I probably should put parentheses around here just so I'm keeping things accurate. Last to say, so this converges to this, but what's our interval? We spoke about this a second ago. It's represented by this power series on the interval from -1 to 1, or from when x, the absolute value of x, is less than 1. Just a recap of this example and these properties before we move on and add some more important properties. First of all, we have this function here. We could have thought about this as 1 over x minus 1 times 1 over x minus 3, but then we would need some property that allows us to deal with the multiplication of power series. We're going to talk about that very soon, but it's maybe not as nice as neat as you maybe hoped. What we did instead, we have a property that allows us to use these summations or differences of a power series. And so we use partial fractions to split up this rational function right here. And then our work was, we have this known power series that we've used a ton. And we're not, again, not even close to being done. We're going to do some even crazier stuff by the end of this section right here in dealing with this singular power series with a lot more properties and manipulation techniques. But what we're doing is writing each of those terms as either the composition, the multiplication of powers of x, or just the multiplication of constants here in composition to create each of those terms. And so I'm just doing, this is kind of like the pre-work of writing each of these in that form right there. Once I've done that, then each of these terms can be represented by these power series following those properties, multiplying by 1/2, multiplying by 6, composing with x over 3. Again, the only difference here being that interval of convergence changes a little bit. But now I have these representations, these two power series for each of these terms, and the sum and difference property says, heck yeah, go for it. You can add or subtract those together to represent those function or those terms that we were working on right there. And importantly, at the very end, all we had to worry about was the interval of convergence. It's not the bigger of the two. So again, that should make sense, right? This power series represents this function just from -1 to 1. This is bigger. This is from -3 to 3. But the intersection of those two intervals of convergences is where we get our interval of convergence for the combination of them.